Okay, so welcome back, everybody. Um, as I mentioned in the previous lecture, our kind of goal here is to skirt very quickly through chapters 5 and 6, really just touching on like exactly what we need in order to discuss the heat equation and Laplace's equation with without having to do too much hand waving. So wanted to avoid like the worst instances of just telling you, oh, like, go check it out to make sure that it works all right in chapters 5 and 6. Of course, when it comes to the chapter 5 and 6 material, if you are interested in any of that stuff, then by all means, have a gander at those at those chapters because they're great. They're nice little self-contained treatments of some of the basics of the theory of distributions um, and Fourier transforms. So if you are interested in those things, then please have a look at them. But for us, we don't quite need so much. We only need a little bit. Um, Here is a nice little quote that I wanted to read just because it's nice. You can find this in the intro little blurb in chapter 5. So this is from Lawrence Schwartz, who was the discoverer of distributions. He actually won a Fields Medal in what I believe 1950. Yeah, he won Fields Medal in 1954 his contribution to the theory of distributions. So here's this little blurb. Thus, physicists lived in a fantastic universe which they knew how to manipulate admirably and almost faultlessly without ever being able to justify anything. They deserve the same reproaches as Heaviside. Heaviside, if I hadn't already mentioned previously, Oliver Heaviside was. He's a very interesting character. He did a lot of amazing. He's self-taught for one thing. He did a lot of amazing. Had a lot of amazing contributions. A variety of scientific applications, and he was criticized often for being a little bit sparse with the mathematical rigor, and he absolutely detested like the axiomatic or axiomatization, I guess I should say, of like math. He very much, he has a really really long diatribe. It's very funny to read against like Euclidean geometry and like axiomatic geometry. But anyway, they deserve the same reproaches as Heaviside. Their computations were insane by standards of mathematical rigor, but they gave absolutely correct results. So one could think that a proper mathematical justification must exist. Almost no one looked for one, though. I believe I heard of the Dirac function. The Dirac delta function is the one he's referring to, the topic, or kind of the main motivating reason for Chapter 5's existence in this textbook. I believe I heard of the Dirac function for the first time in my second year at ENS. I remember taking a course together with my friend, which absolutely disgusted us, but it is true that these formulas were so crazy from the mathematical point of view that there was simply no question of accepting them. It didn't even seem possible to conceive of a justification. These reflections date back to 1935, and in 1944, 9 years later, I discovered distributions. This at least can be deduced from the whole story. It's a good thing that theoretical physicists do not wait for mathematical justifications before going ahead with their theories. So the delta function, so the Dirac delta function in quotes that's being referred to here is something you may have encountered already, but the Dirac delta function, what is it? So it is written as delta not x is something, right? So here we'll see that even this notation that its input is like a real number is wrong. Um, but if we were going to define this, it's 0 everywhere, except at 0 is where the meat is concentrated. So sorry, it's 0 everywhere away from 0, and at 0 is where the meat of this function is concentrated. And here it's suitably infinite. What does suitably infinite mean? Suitably infinite implies that for any a greater than 0, this, I'm again writing quotes here, integral from minus a to a of delta naught of x dx is equal to 1, right? Another formulation that maybe is a little bit more illuminating to what we're actually going to end up doing here. So another formulation is to say that given any function, so given any continuous phi function, so given any continuous phi on, we'll say, this interval minus a to a, that this integral from minus a to a of delta naught of x phi of x dx is equal to phi of 0. So somehow this infinite density at x equals 0, when we integrate it against a function, it somehow picks out this value of the function at 0. So somehow this infinite density at x equals 0 picks out the value of phi at x equals 0 when phi is integrated against this delta naught, this Dirac delta function. Now, what is the bad news here, right? So oftentimes you'll even see this written, so maybe I'll just rewrite it here. Whenever someone mentions the Dirac delta function, you will maybe even see it written literally like this. So it is 0 when x is not 0, and it is positive infinity when x is equal to 0. Sometimes you'll see it written like this, with the understanding that it is normalized in this way so that this is true, or so that this is true. Okay, but there's only one problem with this. As we've written this, we are, suggesting that this is a function of x. It takes in a real number input and spits out an output indicated here. The only problem with this is no such function exists, right? The thing that does this, the object that does this, is not a function. And that's ultimately what the main problem is. So the bad news there is no function that does this. All right? So all of these things we have written in quotes, this is technically nonsense. All right? Which is what Schwartz was saying in that quote that I read, which was that, like, this is just nonsensical on its face. There's no function that has these properties. So, you might say if you're extremely, right, strict about your rigor and you don't like the hand waving, right? And if you're coming at this from a pure math perspective, you probably don't like the hand waving too much. Then you see something like this and you're like, wait, before I can go any further, like, I can't just start trying to compute with this because it's clearly nonsensical. There is no such function, so all this is just meaningless. All right? The key, like, operative word here is there's no function that does this. There is no function of a real variable x, right? A real valued function of a real variable x that does this. However, there is an object that does this, okay? So there is, however, an object that satisfies this role. This object is not a function, but rather is a distribution. Okay, now you have likely encountered the term, like the word distribution in the context of, say, like probability theory and stuff, but this is, we have to be careful here. Like, we have a very specific meaning when we say distribution. So I will give definitions. I will talk about some properties. I'll talk about some basic things, but I'm not going to go too much into the weeds here, because really, while this is all very interesting and it's all very, very important for what comes later in PDE. So if you study PDE at the graduate level, you will talk about the theory of distributions, and you'll talk about weak solutions in the sense of distributions. You'll talk about convergence functions in the sense of distributions. We'll mention that here, but we're not gonna prove too many things about it or whatever. I'm just mostly gonna state things without proof. But our goal is just studying the heat equation, Laplace equation, and being able to do so sensibly. And that requires that I be able to talk about these things, because otherwise, some of the things that you are going to notice just don't quite make sense otherwise, unless we have just a little bit of this background. Okay, so we'll define this later. The key thing is that rather of thinking about a function, right? So key point maybe is that a function takes input, which is like real number, for instance, right? If it's a real valued function of a real variable, and it spits out output, which if it's a real valued function is another real number. Whereas a distribution takes in an input, which is now a function, and spits out a real number. So it's a type of functional type thing in that it takes in functions. Now, that's not the whole story. There's some stuff I have to define here, but this is one of the things. So in this way, it's even funny that in this textbook, he has large print here, where when you think of the Dirac delta function, you think about it being applied to a point x, but really the key point is that you shouldn't write it like this. You should write it like this, suppressing the notation and getting rid of the temptation to think about this as a function. Of course, right? Like, thinking about it as a function can help with the intuition. A lot of the things that you might think are, a lot of the properties you might think are true of the delta function, treating it like a function, do end up being true, but to actually go through this rigorously, justify it, I have to be a little bit more careful. Maybe one question here, right, is to ask ourself, right, like what is, it's like, what is the big deal here, right? What is the problem? Where's the ambiguity? The ambiguity comes in this suitably infinite thing, right? The question is, right, like infinity versus 2 times infinity, right? What is, if here's the delta function, what's 2 times the delta function here? It's 2 times infinity. Should we interpret that separately? Should those two things be equal? It gets really nasty because of this ambiguity introduced here. Okay, but this notion of distributions is going to be crucial to us, because it turns out that we actually need them. Okay, we need them in some way. So what is a natural way in which this thing arises? So natural way that this delta function arises. Recall from ODE the Heaviside function. So the Heaviside function, of course, you thought of as a switch. This was very, very useful for dealing with piecewise forcing terms, for instance, right? If you had a piecewise forcing term, it was typically better to deal with that, especially if you're going to apply something like a Laplace transform. It's typically better to deal with that by thinking of it as a linear combination involving Heaviside functions, where you switched on pieces of the function that were turning on, and you switched off the other pieces of the function. So what was the Heaviside function? The basic Heaviside function is the following. It is just the piecewise function that is 0 when x is less than 0, and it switches on at 0. Right, so it is constant 1 after that. And so, if we look at a picture here, right, what does this thing look like? Well, it is 0, right, up until 0, and then it swaps on here, and it is constant 1 from that point on. This is the Heaviside function. So again, this was very useful in ODE for dealing with piecewise forcing terms, and in fact, you like depending on the problem involved, your solution could involve Heaviside functions, right? Okay. So then the question is, what is this thing? What's the derivative of the Heaviside function? Well, you could say, ignoring this point where it changes, everywhere here it's constant, so its derivative is 0. Everywhere here, again, ignoring this point where it changes, is just a constant function 1. So everywhere there except at 0, it's 0. And so what this thing is it is 0 at when x is not 0. But then when x is equal to 0, well, this function's not even continuous here. I mean, it's not continuous there. It's certainly not differentiable there, right? And so what happens here is that this derivative is undefined at x equals 0. But let's think about this kind of like physically. Let's kind of use our intuition here. Imagine the Heaviside function is describing like displacement or position of something, right? Right. So here I have constant 0 value for the Heaviside function. At x equals 0, this instantaneously changes, right? This is not a gradual change. It's not a continuous change even, right? You go from infinitesimally, as you're very, very close to 0, you're still at 0. But then the second you hit 0, instantly, you are up here now. And of course, I could have scaled the Heaviside function to be whatever. It could be 0 to the left of 0, and then it could be 1 million here, right? So that change is even more extreme. But that's not really the point. The point is that I am instantaneously changing, right? Instantaneously. Boom. So, yes, this is undefined, but in a sense, right, it makes sense to say that my Heaviside function has a derivative that in some sense is like this, right? It's 0 when x is not 0, and then it's like plus infinity when x is equal to 0. Because it like instantaneously changes. Of course, there's ambiguity here, right? There's ambiguity here. This is not really a well-defined function. But this is kind of the thing that lets me know, oh, wait, like this idea of thinking about what it is that's happening here. This indicates, sometimes you'll hear the delta function referred to as like an impulse function, where there's nothing and then all of a sudden, boom, right? An instantaneous concentration. That's kind of what is being denoted here in this derivative of my Heaviside function. So this is one way of like motivating how we could think about this as a function delta naught, right, of x. This is one way of thinking about this. Now, how to justify, like how to view this, we'll kind of get into that. I'm not going to go too much more into the intuition, but this is at least giving you like a very basic example of like where this thing might arise from naturally. Okay. Another way to see this arising is the following sequence of functions. So a sequence of functions that concentrate in the limit. So what is this? Here's an example. Take the following sequence of functions. So f sub n of x is defined to be n minus n squared x when when x is between 0 and 1 over n. And it is n plus n squared x when x is between minus 1 over n and 0, and it is 0 outside of this window. Okay. So again, this might seem like a pretty complicated thing. If you actually do this for a few values of n, you'll see that this is not nearly as complicated as you might first think it is. I'm going to show you a picture here in a second. All these are steeper and steeper kind of like spikes, right? Steeper and steeper like spike functions. Okay. One thing to note is that for all n in the natural numbers, the integral from minus infinity to infinity of this sequence is 1. So these kind of encode that thing that we want to be true, the thing that helps us kind of tell what is a sensible delta function is this condition. All right. Well, here's the question. If we consider the limit as n goes to infinity, what does this thing converge to? Converges pointwise to a function. It seems like that function is 0 when as n goes to infinity. This is basically every point except 0, right? Is 0. And what is the value of the function going to infinity? Right? This is equal to my delta function. Right? So this thing converges pointwise to a function that mimics the delta function in this way. Okay. And the question is, can I expect the limit function to have the same property? The problem is no way to do this without ambiguity. So no way to do this rigorously without ambiguity. So although these are good, like intuitive kind of models for what the delta function we think is doing, again, function here. Actually, the fact that it's not a function is really coming back to bite us, because that's exactly why we can't treat it in this way. That's exactly why there's no hope for being able to do this in a completely unambiguous way. If you wanted to see what a few terms in this sequence of functions look like, here. So there's f sub 1, f sub 2, and f sub 3. You can see exactly what's happening. As n increases, this is beginning to concentrate more and more at 0 to infinite concentration of this in the limit. Oh, let's see. So there we go. Okay, so that's another thing. So what is the idea then? Right. So here's, how did Dirac think about this thing? How did he attempt to do away with ambiguity? He wasn't 100% successful. How did he think about this? So here is Dirac's own quote on it. So to get a picture of delta, take a function of the real variable x, which vanishes everywhere except inside a small domain of length epsilon, say, surrounding the origin x equals 0, and which is so large inside this domain that its integral over this domain is unity, is 1. The exact shape of the function inside this domain does not matter, provided there are no unnecessarily wild variations. For example, provided the function is always of order 1 over epsilon. Then in the limit epsilon goes to 0, this function will go over to delta of x. So the idea that sort of formalizes this, right, is passing to integration. So the idea here is we want to pass to integration in the sense that integration we think of as an averaging, and we think of integration involving these things as being a little bit better defined, right? This idea that we had initially turns out to be a very good one. This O. If instead of maybe just thinking about these properties on their own, I focus on what it does to some other function, we'll say a test function, that it picks out this value, this is a nice way of thinking about what's going on here. The only issue is that, as we've seen, the bad news is no function does this. Okay, but there's an object that does this. Okay, and that object is called a distribution. So then what is the idea? So first, we have a class of test functions. These will be functions that are smooth on R with compact support. So we've mentioned compact support before. Smooth with compact support. So vanishing off a compact set, right? So vanishing off some compact set, say omega. Okay, we'll denote such functions as phi. We'll say they belong to the class of C infinity functions defined on the reals with compact support. That's how we denote that. So this little sub C is compact support here. Okay, so that's the first thing. So question is, how many such functions are there? Can you even give me one? Right. So remember, what I wanted when I talked about a function with compact support, I was wanting something that like looked like this, right? It was 0 and then it was something like that and then it was 0, right? Or maybe it was something like, maybe it was very much more concentrated. But the idea is it's smooth everywhere on R. There's no corners here. So it's not piecewise in the sense that like at these points where it zeroes out, there's some kind of corner. No, no, it's smooth everywhere. This is completely smooth. Okay. So you might struggle, looking at this, you might struggle to come up with even a single example, right? If you, for instance, try to use like a polynomial function, you're not going to get anything that looks like this, right? It's polynomials don't, their graphs do not look anything like this. So then is there even a single function that looks like this? Actually, there's plenty. So there are plenty. Here is a basic one. So what is this basic test function? This is called a bump function. Let a be just a constant parameter here because there are different bump functions for different values of a. Let's define this phi sub a to be e to the minus 1 over a squared minus x squared if the absolute value of x is less than a and 0 otherwise. This is referred to as a bump function. Maybe this is even like the canonical bump function. And what does its graph look like? It actually looks like this. In fact, you can see, here it is. There's the graph. That's exactly what it looks like. You can check that yourself. Different values of a give you different bumps. So there's a lot of these, right? So it's not a question of whether or not there exists enough of these. These are my test functions. They look, something like this, right? This is kind of like the ideal form of them. Okay, these bump functions. But there's plenty of these, okay? So there's plenty of these. So to say that, I seek out test functions in this class, there's tons of stuff to pick from here. So that's important. That's good. But guess what? Because of the smoothness here, if I have a function that's in C infinity with compact support, then its derivative is also in C infinity with compact support. That's nice. Okay, so differentiating doesn't take me out of this class of functions, right? It's in the same class of functions. And so, the idea is to do the following definition. Okay, a distribution f. Okay, again, this distribution is also can be thought of or sometimes called a generalized function. Okay, is a rule assigning to each test function phi in the class of C infinity functions with compact support defined on R a real number such that this rule is linear and continuous. Linearity, you always kind of know what that means, right? So if you think about this as an operator, then the thing is going to be linear in some relevant slot that it operates in or on. Continuity, I'm not going to worry about too much because whether I describe it, loosely or precisely, in terms of like uniform convergence of things, I'm not going to worry about it too much. Just the loosely thing is that if you take two test functions that are close, keep in mind the test functions live in this space of functions, so you'd have to have a notion of an inner product or a thing that lets you know how to measure the distance between functions in a function space, right? So if you take two close by test functions, then the output applying f to each of those is also close. That's the continuity thing, and that's as precisely as I'll state it. The linearity argument we'll see in a second. As a rule, if I think of f being defined, what does f take as input? So the input of f is some test function phi, and the output is some real number r, right? Whatever this output is, the notation that denotes this thing is bracket f phi. This is the action of my distribution f on the test function phi. So for each phi, my test function, this number, or this thing, is a number. It's just a real number. It is the real number I get from f being applied to phi. So now I can state what linearity means. So linearity means if I have a linear combination of phis here, so let's say if I take f and I apply it to a phi plus b c, then what I should get is a f phi plus b f c. So that's the linearity. The continuity is, as I said before, right? Close by phis that are different lead to close by outputs. Okay. Now, one example. Integration as a functional. So consider f sub 1 as the functional that assigns to each test function, say phi in C infinity with compact support on R, its integral over R. i.e., this f sub 1 acting on phi is the integral over all of R, so from minus infinity to infinity, of just phi of x dx. I know this is a well-defined real number because this thing has compact support. So this is integrable. It's as nice as possible, right? It's this thing is bounded. This thing's going to spit out a number, right? So there it is. Right? This is a distribution. Why is this a distribution? So this is a distribution that if the functions are close, the integrals are going to be close. That's the continuity part. Don't worry about that. Linearity comes how? Linearity comes from linearity of the integral, right? We know the integral is a linear object, linear operator. So this is a distribution because linear, continuous, and it's a rule that assigns to any test function here a real number given by its integral. So this is an example of a distribution. So there's one. You've already been dealing with examples of distributions your entire mathematical career since calculus, right? Okay. What next? Well, next, let's think about uh, a similar thing. So another example, treating a function, a locally integrable function, as a distribution. So what does this mean? So let f be locally integrable function. I'll talk about what that is later. On R. Then f, I mean, I could just take this to be integrable and make it easier, but we'll say that this is locally integrable function on R. Then f of x can be interpreted as a distribution big F sub little f via the rule that assigns to a test function phi its integral against little f. And this is continuous and linear for the same reason our previous example was. This is called, so big F sub f is called the distribution generated by the function f. Now, this also hints to us part of the power of the distribution itself. Note, here is the power of the generality slash, you want to call it like floppiness, of the fact that you've passed to integrals here in these examples, right? Two functions can generate the same distribution, right? If I take little f sub 1, and it is the function, say, x cubed, and I take little f sub 2, and it is the function, say, x cubed, if x is not equal to 7, and it's 5 at x equals 7. These two different functions, right? So they agree everywhere except at this point. Of course, I could have done this for a few points. I didn't have to do it for just one. But these are definitely different functions because they don't have the same value at x equals 7, right? This would be 7 cubed. This is 5 at x equals 7. These two functions generate the same distribution above. So you're losing some point-wise details here to instead get like a more generalized or more averaged picture here, because this involves an integral, right? Okay. And so, how can we finally make the delta function precise? How can we make the delta function precise? Here's how. The delta function, delta naught, is the distribution defined by the rule delta naught phi is phi of 0 for any phi in my class of test functions, C infinity with compact support. Remember that very first idea we had, right? Or maybe it was like our second idea, right? Our alternative way of thinking about it. Where do I know I have it somewhere around here. Let's see. Ah, yes. Yeah. Here. We said, yes, there's no function that picks this out. Ah. But there is a distribution, right, delta naught, which for any given test function, its action on that test function is given by, it's just the thing that picks out the value of the test function at 0. Okay. And so we, of course, have picked 0 here, but we can also, so similarly, the delta function, the normal delta function is, we would say, concentrated at 0. We could talk about this concentrated at any point, x naught. So the delta function concentrated at x naught is the distribution defined by, it's the thing that when you pair it in this way, you have it act on a test function, it picks out the value of that test function at the point x naught. Right, this is not like a partial derivative of delta, whatever. So this is for any test function. And so, with this definition in hand, we don't have to write scare quotes anymore. We can actually just say it's a distribution. These are distributions. They're not functions, they're distributions. So we could call it the delta distribution, but delta function is kind of, and it kind of has a nicer ring to it. It's just that it's not really a function. The main thing to take out of this, when we think of the delta function, we don't think of this, because that indicates it takes in like a real number input. We just suppress that entirely and write it as delta naught. So my delta function is the distribution defined by this rule. Okay. Now the chapter 5 continues here by going on to define like how you can differentiate distributions and all kinds of properties and formulas that arise from this. I'm not going to do that. I just wanted to put this delta function on solid footing. So now it is. So moving on. Moving on, I will very, very quickly talk about the Fourier transform. So in chapter 6, Fourier transform. I just wanted to define this, talk very, very little about it. I will periodically be returning to discuss this a little bit as it becomes more clear kind of what's going on behind the scenes. The main reason I wanted to at least mention it first is that the first explicit formula we're going to get for the heat equation is going to be derived via the Fourier transform. I'm not going to do that derivation, but I wanted to at least mention what the Fourier transform was before saying, oh yeah, this is done by Fourier transform. And so, what is the Fourier transform? First of all, if you need a little refresher here, right? If I have a complex number z, and I can think of this as having real and imaginary parts x and y, can identify the complex numbers with, for instance, R2. Of course, because of how complex number multiplication works, this is not quite the same as R2, although pictorially I can certainly, refer to them as being represented by the points in the plane. If you want to think of here, I'm not going to worry too much about we're not going to talk about complex valued functions or whatever too much. We're merely going to focus on real valued functions, so functions of a real variable. Um, but so for us, we are happy to write, whenever we think of a function of a complex variable, we're actually happy to write it in the form like f1x plus f2x times I. So a real and imaginary part to this function. The way that integration works for this is strikingly similar. If you haven't had Math 463, if you just took my Math 463 course over the summer, then you'll be happy with all of this stuff because you'll have dealt with this in, in depth quite a bit. But if not, then you can either refer to my Math 463 videos, or you can just take my word for it that a lot of this stuff works similarly, and for our purposes, we don't really need to worry about it too much. Okay, at any rate, the exponential function e to the z is straight up just defined to be its power series expansion. So sum from n equals 0 to infinity of z to the n over n factorial, right? All of your favorite properties of e are preserved here by just defining it to be this thing. Okay, no reason to reference logarithms or anything like that, just define it to be that thing. We get all of our favorite properties of this thing. There is, of course, Euler's formula, which you may have seen in several contexts, which is to say e to the ix can be expressed as cosine x plus I sine x, right? Leading to everyone's favorite formula relating fundamental constants, right? E to the I pi plus 1 is equal to 0. So you can get a variety of similar formulas out of this. This is very important. This is especially going to come into play later when we're doing separation of variables and you ask yourself, hey, these Fourier series, me expressing all these functions as linear combinations of sine and cosine, what's the deal? Why sine and cosine? The answer is hidden in this formula right now. Okay, so you won't see exactly what I'm talking about until later. There's a notion, of course, of complex conjugate. So z bar is the complex conjugate of z. This would be x minus iy. You can do some things like, for instance, considering the conjugate of e to the ix. That's because e to the ix is real and imaginary part written here. This is actually just cosine x minus I sine x, which is the same thing because cosine and sine are even and odd functions respectively, right? This is just e to the minus I x, if you like, right? This is the same thing here. Okay, actually you don't even need that. This is just e to the minus ix. Okay. If I wanted to know what is the derivative with respect to x of this quantity, e to the ix, it's exactly what you think it is. Hey, right? Math 463 not required. It's exactly what you think it is. Okay. Now, I mention all of these basic things so that when I write out the Fourier transform, it's not totally a mystery. So what is the Fourier transform? So let f of x be integrable, real valued on R. What does integrable on R mean? This means that if you integrate it over R, integrate its absolute value over R, that is finite. Okay. Then, my definition for each k in R, define the Fourier transform of the function f be f hat of k is defined to be the integral from minus infinity to infinity of f of x e to the minus ikx dx. That's it. Immediately, you're going to be yelling at your screen, hey, wait a minute, I've seen exactly this thing before. Well, maybe not exactly this thing, but I've seen something extremely similar to this thing. In fact, if I were to change this ever so slightly, right, if I were to get rid of that I, then what the hell is that? Oh, that's actually the Laplace transform, right? So this is very similar in spirit to the Laplace transform. Okay, but it has a lot more uses, a lot more properties that are super duper nice. Although, like I said, it does share a lot in common with the Laplace transform. In fact, it is just the Laplace transform, except instead of, if my Laplace transform variable was k instead of, usually it's s. If my Laplace transform variable was k instead, it's just ik, right? It's the Laplace transform of ik plugged in instead of just k. So, so it is very, very similar in spirit to the Laplace transform. This is the Fourier transform. Okay, so this takes a function of x and transforms it to a function of k. K is still a real number here. Sometimes this is written as like Fourier transform of f is f hat, or like we did for Laplace transforms, like Fourier transform of like f of x of k, right, is f hat of k. But for the most part, where there's no confusion here with this operator, it's just f hat. Okay. Now, let's cheat a little bit by thinking back to the Laplace transform, since it's something we've already done here, right? And I don't need to do any further derivations. Why was the Laplace transform nice? Laplace transform was nice because we applied it to an ODE to transform ODE from a differential equation to an algebraic equation. And algebraic equations typically are easier to deal with, right? At least the ones that we dealt with in that way were easier to deal with. We did some algebraic manipulations of those things, but those algebraic manipulations relied on the fact that the Laplace transform of derivatives of a function had a very, very nice property, okay, that allowed us to apply them to differential equations. The same thing is going to be true for Fourier transforms. The Fourier transform of derivatives has a special form, okay. Then we, did our manipulations in this transformed universe, and then the whole point, the reason why we were able to use Laplace transforms to solve anything, was that there existed an inverse Laplace transform, right? The inverse Laplace transform took us back to the world that we started in and allowed us to write out our solution in, to the original equation, the original differential equation, and we could write it out entirely. And what was nice about it is it just spat it out. It didn't have to do anything. There was no solving for arbitrary constants, none of that stuff. It just spat it out. So in the same way, Fourier transform has extremely nice properties. Specifically, how it transforms derivatives. These are nice. And has an inverse Fourier transform. I'm not going to go into that because I don't need it yet. When I do need it later, I'll refer to it. But it has an inverse Fourier transform that undoes this process. Okay. There's a lot of really, really cool videos people have made discussing the Fourier transform, how to think intuitively about the Fourier transform. Probably one of the most common interpretations you'll see is like listening in music, right? Listening to music. If you listen to music, then technically the process that ends in your brain interpreting those sound waves as music, right? You hearing music, process that is undergone there is actually a Fourier transform. Okay, the Fourier transform has transformed those harsh sound waves, okay, into information that your brain interprets in terms of volumes and things like that. And so you hearing music out of those sound waves, those disturbances, is a result of a Fourier transform taking place, basically. This is probably one of the more common explanations of this thing, and it's a good one. It's a really good one, very satisfying. So, like I said, I'm not going to get stuck in the weeds of Fourier transform properties. When we need properties, we will return to this stuff. So I just wanted to show you the form that this takes. Even just showing you this little bit I did, which is literally 2 pages worth of stuff, right? Like, huh? It's basic, like, basic scribblings on complex things that I needed to write out the Fourier transform. And here it is, okay? This, even just what I've written here, will make a return later in the course. And you'll say, ah, so that's the reason for the sines and cosines. Okay, I have one more thing that I want to define that you may have seen before, depending on your background. So one more thing. So this is the definition of what's called convolution of functions. You have potentially seen this if you've taken a probability theory course. It may not have been defined exactly in this way. There's a version of this for discrete random variables, but you know, we're in continuity land, so we're not going to talk about that. But what is this? This is a type of multiplication of functions. It's not quite that, as you'll see. It's actually, in terms of multiplication of functions, this is far more convoluted, pun totally intended, version of multiplication of functions, right? If you're thinking of like pointwise multiplication of functions, right? That's a much simpler thing than what we're going to do here. So what is the convolution of two functions? If f and g are functions on R, their convolution is written f star g, f asterisk g, is a new function defined on R via the following formula. So f star g of x is the integral from minus infinity to infinity with respect to a dummy variable y of f of x minus y g of y dy. You might say, wait, what is this? So when this integral is taking place, this x is fixed. Right, so for the purpose of this integration occurs with respect to the variable y, and x is fixed. Okay. Why am I defining this? So what is this? And the answer is, it turns out many solutions to PDEs, important PDEs even. Okay. Are given in terms of a convolution of functions. So it is better to think of the intuition here as running backwards, where you first solve the the equations, and then you notice, oh, actually this equation takes on this particular form, and very commonly I can write that in this particular form. You've already seen some examples of this kind of thing happening in ODE depending on how much your instructor did with Green's functions. So if your instructor did a lot with Green's functions, then you've already seen some form of this sort of thing happening. But here's how this works. This is actually kind of a complicated way of multiplying functions, right? It's not that simple. So even like some basic properties might be a little bit confusing at first, but they actually work out in this way. You can verify some properties that convolution has. So just pick your two favorite functions and try to compute this, and you'll see that this can be really kind of nasty. But what are some properties that this thing has? So it doesn't actually matter which order you convolute the functions in. That's not really that obvious just looking at this formula, but this is true. What is the derivative? So this is one property. Here's the second property. What's the derivative of a convolution? Say with respect to x. What is this? It turns out this is the same as the convolution of the derivative of f with g. But actually, it turns out that this is the same as the derivative of the convolution of, sorry, it's the convolution of f with the derivative of g. So looking at it this way, when I take the derivative of convolution, I can put this derivative on anything I like. This property involves the convolution in something known as mollification. Now, we're not going to talk too much about this. The idea behind mollification, to mollify something, right, literally means to smooth it. The idea behind mollification is if you take a function of questionable regularity, right, a function that you don't like how many derivatives it has, right, maybe you don't think it quite has enough, you can convolute it with a smooth function that has infinitely many derivatives, and in doing so you create a function that incorporates that function. We'll say that f is the one that doesn't have that many derivatives. It incorporates that function here in the new function, but it adds regularity to it in the sense that now this new function, when I take a derivative, I can put that derivative on the smoother function, right? The function that has a lot of derivatives. And so I have added regularity. I've added derivatives to the function in question. This is known as mollification. This is important conceptually for a variety of reasons, but I'm not going to talk too much about that. I just wanted to define this so that we could talk about this later. Another thing, if we talk about the Fourier transform behaves well with respect to convolution. If I take a convolution of two functions and I take its Fourier transform, that is actually the product, pointwise product of the Fourier transforms of the functions. So in the world of Fourier transforms, this convolution is actually literal pointwise multiplication of functions. It's just pointwise multiplication of the transformed functions, right? The functions that have been hit with the Fourier transform. And so you might have looked at this and said, wait, this is not quite what I have in mind when I think of multiplication of functions, but in the world of Fourier transforms, it is a multiplication, okay, in a sense. Okay, so convolutions allow you to smooth out functions. That's what this mollification is. You can smooth out functions in this way. All right, though. But now we'll pick up here in the next lecture, but I want to at least get it down on paper just because I think that'll be a lot more satisfying. Let's at least write it down on paper so that we can be happy. So, and now, at last, we arrive at the heat equation. Now, as I have already mentioned, the author, the textbook, really likes to refer to it as the diffusion equation instead, which is perfectly fine and probably the better thing to do because it illustrates that it really arises in a lot of different situations other than heat flow. But the general idea is that you have a quantity, U, that is diffusing in some way. We'll talk a little bit more about what we mean when we say it's diffusing later. One example of this diffusing is one of the early papers of Einstein when he wanted to discuss Brownian motion, right? This diffusion equation could be thought of as kind of modeling the probabilities for positions of a particle, and this particle's undergoing this kind of random motion, Brownian motion. And that is particularly something that is nice to think about because when you see the fundamental solution to the heat equation, if you haven't seen it before, then you are going to look at it and you're going to say, wait, I know what this function is. Like, I know exactly what this thing is because I've seen it in every statistics and probability course I've ever taken. So I know that somewhere lurking in this equation is a description of probability. So what is the 1D heat equation? This is U sub t is equal to alpha U sub xx, where alpha is some constant here. So alpha is some fixed positive constant, right? So n-dimensional heat equation can be given in terms of the n-dimensional Laplacian. Again, it's U sub t is alpha times Laplacian of u. These are my heat equations. So this is what they look like. Okay, so let's look at the 1D IVP for the heat equation. This would be U sub t is alpha U sub xx. Alpha is some positive constant, and say we're solving it for x on, I don't want to imply that this is like a variable. Let me get rid of that here. All right, so we're solving this for x from minus infinity to infinity, t greater than 0, and we have some initial quantity, right, some initial data, we'll call it g of x, right, and this is for x on the reals. So here's my heat equation IVP. Okay, I'm not going to derive where this comes from, so you can, one derivation is Fourier's or Fick's law to derive this. It's actually pretty quick derivation. There's other derivations done in the textbook, but I'm mostly going to dive right into this and how to solve it because we're going to see exactly how this relates to the things that we've been talking about, today, which was distributions and convolutions and Fourier transforms. So first of all, the explicit solution, we're going to get to this, the D'Alembert type solution, if you like, that we're going to get out of this is the easiest way to derive it is via Fourier transform. I'm not going to do that, but I'm just letting you know that it's the Fourier transform applied to this that really gets us the solution. So anyway, that is where we'll pick up next time. So until next time, I will see you.